Good afternoon, everybody. Today we'll be talking about our third formwork design presentation. We'll be talking about design of walls and columns formwork. The major issue when we talk about the difference between designing a formwork for a wall and a column than designing a formwork for a slab is the load. The design itself, it will not differ at all. So you will follow the same design procedures that we talked about last time. However, the question here is whether the concrete is fluid or solid. So the degree of fluidity of concrete. So if concrete is fluid, if you deal with it as a fluid, then the pressure that it will be acting on the formwork would be simply the unit weight multiplied by the height, hydrostatic pressure. So this is simply the pressure. It's linearly increasing from 0 until reaching a value of W times H or gamma H. However, this is the most extreme situation. But if it is a solid, it will be something very much less than that. So researchers made some relations based on statistical correlations, and it came that there are several factors that govern the issue of fluidity of concrete, whether it's fluid or not. First is actually the unit weight itself. Then something related, it's called the chemistry coefficient, related to the chemical composition of the concrete, and we'll be discussing in details what is it, and the rate of fill of concrete in form, and the temperature of the concrete within the form. However, the upper bounds and lower bounds of these formulas are a minimum value of 600 times CW. This is based on pound per square feet units, and the maximum is W times H. However, these equations are based on something very important, that it could apply only when the slump is 7 inch or less. 7 inch, it's 17.5 centimeters. So when you think about it, so if the slump is more than that, that means that it's more like self-compact concrete. It's very fluid actually. So if the slump is more than that, you should simply say that the pressure is W times H, because that's it. I mean, it is a fluid actually. Self-compacted concrete is a fluid. However, that equation that you could see here, it is for a case for a wall form where the placement rate is less than 7 feet per hour and the placement height is less than 14 feet. However, if one of these two conditions is not satisfied, you'll have another equation. And again, these two equations are based on statistical correlations of hundreds of experiments that were done on concrete forms, measuring the pressures along their heights. Now, what is the weight coefficient and what's the chemical coefficient? The weight coefficient is simply based on the idea that the average concrete will weigh between 140 to 150 pounds per cubic feet. So if it is between 140 to 150, then the value of CW is simply 1. However, if it is less than 140, you will factor it down. If it is more than 150, you will factor it up by W over 145, and if it is less than 140, you will factor it down by 0.5 times 1 plus W over 145, but should not be less than 0.8. However, the other factor which is very important is mainly related to the issue of admixtures. So whether you use admixtures or not. So if you don't use admixtures at all, then the factor is simply 1, which is the case in most of the cases that we could see. However, if you use chemical admixtures, retarders or superplasticizers or whatever, the factor will be 1.2. If you use mineral admixtures with certain percentages, the ones shown that you could see here, you will use a factor of 1.2. However, if you use both chemical and mineral admixtures, then the factor jumps up to be 1.4. So this will tell us that the more admixtures you use, the more fluid is the concrete, which is making a lot of sense, because actually self-compacted concrete is a concrete that's full of admixtures. So at the end of the day, or high performance concretes, all these concretes, they are full of admixtures. So you must understand that this will increase the fluidity and it will increase the lateral load on the formwork, whether wall formwork or column formwork. That takes an example. So if I have a wall form that's 12 feet high, filled with 150 pound per cubic feet concrete at a temperature of 70 Fahrenheit, the concrete is type 1 without a retarder. Concrete will be placed with a normal internal vibration to a depth of less than 4 feet. The rate of placement is 5 feet per hour. So according to that, we'll get our factors. So CW is simply 1 because it's 150 pound per cubic feet. We have no admixtures used, so CC is 1. And because our conditions are satisfying the first condition, then we are talking about the chemistry coefficient multiplied by CW times 150 plus 9000 R over T. So this will give us 793. Now we should check the lower bound and upper bound. The lower bound is 600 times 1, so it's 600. The upper bound is W times H, which is 1800. So we are in between the two boundaries. So we will use our number, the 793, and this will represent that shape. So the load will have a lateral load that has a trapezoidal shape. So now we are talking about something that it will reach the maximum at 5.3, and it will maintain this maximum until the full depth, and this 5.3 feet is calculated based on the ratio between 793 and 150. Then if we talk about columns, the situation for columns is very similar. However, it's simpler even, because the loads on columns are even smaller, because the four sides of the column will work with us to carry the load. So it's only one equation. It doesn't have this condition. It's only the first equation, and the same chemistry coefficients, the same weight coefficients are used, and again the same boundary conditions should be respected. The minimum is 600 CW and the maximum is WH. So if we have another example, a 14 feet high column is filled with 150 pound per cubic feet concrete at a temperature of 50 Fahrenheit. The concrete is type 1 without a retarder. Concrete will be placed with normal internal vibration to a depth of less than 4 feet. The placement rate is 7 feet per hour. So again, the CW is 1 and TC is 1. So we'll apply the equation and we'll get a 1410 pound per square feet. Then again we are between the two boundaries, the upper limit and the lower limit. So when we draw it, again we'll have a trapezoidal shape. However, the depth here now, the depth of the maximum limit, the maximum value, sorry, the value of that we have calculated is the 1410 is 9.4 feet, which is based on 1410 over 150. So this is 9.4 feet below the top of the form. Thank you, and that's it for this presentation for the compulsory part of it. However, the other is the commercially available forms or the patented forms, which, as you could see here, you have patented systems like the ones we discussed before. However, these ones are for walls mainly, and they could be based on a lot of different designs. So you could have maybe two sets of lateral supports, or three sets, a set of three lateral supports depending on the height. And this thing again, depending on the different loads, you will have different configurations and different dimensions, and the catalogs will help you to pick the ones that you could that are suitable for your option depending on your load.